Okay, so I want to talk about a couple of climate models that I'm learning about on Coursera, a course from University of Chicago. It's about modeling climate change, and it starts with very simple, elegant models of understanding how to predict the temperature of a planet based on the atmosphere, what's in the atmosphere, based on different weather patterns and things like that. So it's very cool stuff. So I wanted to have this video to explain the very basic models that they start with, and I recommend that you go watch that course to learn more about this. It's kind of cool stuff. So the basic idea is we have here a planet. Let me go full screen. So we have a planet. Let's make it like this. Okay, so we have a planet, and the planet is receiving radiation, right? It's receiving energy from the sun, and that energy from the sun, that's the only source of energy that's really contributing to warming up the planet. That's approximately true. You might have energy from the center of Earth that's coming from radioactive decay in the center, or it's coming from the original gravitational collapse of Earth. So that caused heat when Earth formed, and there's some of that energy left over, but that's very negligible. So for now, the incoming energy that's determining the temperature is just this from the sun, and it has a number. We call it S, solar constant. That's how much energy in watts, that's an rate energy per unit time, that's coming as light per unit area. So the more area you expose, the more energy you're getting. So that's the number. It's approximately 1350 watts per meter squared. So if you had a solar panel 1 meter squared, you'd be getting 1350 watts or 1350 joules every second. Okay, and then the simplest model is called the bare rock model. So that's like bare. Okay, so the simplest model is called the bare rock model. That means you just have a rock. That rock is absorbing this radiation and then emitting it back into space. So the way that you predict the temperature is to say the power, or the power in, whatever goes into this rock, equals whatever is out. Because that's when the temperature stays constant. If you're getting more input power than you're emitting, then your temperature is actually currently increasing. If you're emitting more than you're receiving, then you're cooling down. So when those two things are equal, that's when you reach a steady state in temperature. So this one, the N, that's what's coming from the sun. The way we would write it is S, that's per unit energy. That's the fraction of, that's how much energy is coming in, and that's hitting the surface of the Earth. A fraction of it, we're going to write it as 1 minus alpha. Alpha is about 0.3. This is called albedo. If you can imagine, if that light is hitting a mirror, which is perfectly reflector, it just bounces back and you don't absorb anything, and you stay cool. So a perfect mirror would basically just not warm up. But if you absorb energy, that fraction of energy that you're absorbing is this 1 minus alpha. That's how much energy is coming in, times pi r squared. Because this is energy or power per unit area, per meter squared, and then we multiply it by this area over here. That's the area of the projection of Earth, the shadow that the Earth is making. So how much light, the area that's absorbing light, that's pi r squared. And that's equal to the energy that it emits. And this is called the Stefan-Boltzmann law. So we know if something is at a temperature, Like, if you heat up an oven, it's red hot. That red hot is because it's hot, and at a given temperature, it's emitting light that we see as red. At the temperature that the Earth is at, it's not as hot as 1,000 degrees, so it's not red, but it's still emitting. And that law, the amount that it emits is called sigma. That's Stefan Boltzmann constant times T to the 4. That's just a measured law that the higher temperature you are, the more power you're emitting, and times the area, total surface area of Earth. If you assume it's a sphere, then you get 4 pi r squared. And then these r's cancel, they appear on both sides, so they don't affect the final temperature. And then we could say like temperature to the 4th of the ground is equal to S1 minus alpha over 4. 4 is that from the surface area to times sigma. Sigma is a Stefan Boltzmann constant. It's about like 6 times 10 to the minus 8, I think, if I remember correctly, approximately, so we can look that up. But then I calculated this number earlier. It actually comes out to be something like 250 Kelvin, which is minus 18 Celsius. So that's really cold. And the Earth is not as cold as that. And the reason is because there's an atmosphere. So we can actually refine the model and get something like this. So we have this. The Earth is here. And then we have the incoming radiation. And there's also an atmosphere. How should we draw the atmosphere? Let's just say like this. There's an atmosphere. This layer that's causing a kind of a greenhouse effect. And so what is a greenhouse? A greenhouse is something that lets in visible light that's coming from the sun. So this yellow light will arrive at Earth and warm it up. And then Earth will still emit this radiation here. So Earth is still going to emit some radiation at a temperature of the ground. And it's still absorbing this factor from the sun. But now this atmospheric layer is absorbing the radiation that the Earth is emitting. So it gets absorbed in the atmosphere. The atmosphere warms up, and then the atmosphere itself starts emitting. Emits some of it back outside into space, and some of it just goes back to Earth. And that's what causes the extra warming, is that instead of just this black radiation going into the space, some of it actually gets absorbed in the atmosphere and re-emitted back. So it causes some extra warming. So if we wanted to calculate how much that would be, we're going to modify this equation. Now what goes into Earth is S1 minus alpha over 4. That's the factor from the radiation, plus the sigma temperature of the atmosphere to the 4. Now that's equal to the T ground times sigma, also to the 4. So you see, actually, there's compared to what we had before. Let me just divide by sigma here. So this cancels, and then I have a sigma here. And so I just divided by sigma on each part of the equation. So now, compared to what we had here, we had the same term, contribution from the solar radiation, but there's also some light that's coming back to you from the atmosphere. That causes some extra warming in the ground. And when you actually calculate this, you get, this is becomes, I think, 30 Celsius. So you have now 30 Celsius as the average temperature that you predict with this atmospheric layer that's sort of perfectly absorbing. And when you look at the actual real global temperature, it's somewhere in between these two. It's not neither extreme. It's not like you're absorbing everything or emitting everything. Here you're absorbing all this black stuff. Here you're emitting it all into space. The actual current Earth is somewhere in between, and I think the average is 15 Celsius. But I just thought it's pretty cool that there's just basic model. All you need to know is the Stefan-Boltzmann law and the fact that there's a fixed amount of energy flowing through from the sun. You can predict the temperature of Earth and get roughly a correct answer. And of course, this is the basic model. Then you start to add atmospheric phenomena and understand like how air moves around it, other ways that heat flows through convection, through movement of wind and atmospheric phenomena. And then that gives you more and more accurate or more and more complicated models. And you might be able to explain this 15 Celsius better. And it all depends also what kind of gases you have in the atmosphere, because that determines how much of this black stuff you're gonna absorb. So if you have more CO2, you're gonna absorb more radiation at the wavelength that the CO2 likes to have. If you have water, this is what you get in Venus. Venus actually, instead of heating up to 15 Celsius or 30 Celsius, is actually like 700 degrees. And so it's very, very hot because of runaway greenhouse gas effects. So you warm it up, things start to evaporate, you get even more and more of these layers, you get many layers, and that causes the temperature to go way up in Venus. Even though it's albedo, it's reflection, it's very reflective, so it doesn't take a lot of this incoming radiation, but it's the part that it takes stays there because of the greenhouse gases. Okay, and another thing it's not just about, and you could understand more than just Venus and Earth. You can also look at the moon. The moon is different in that it doesn't have an atmosphere, so when the radiation comes, like it comes like here, it sticks there, and it doesn't really transfer through convection and through the atmosphere. So it has a slightly different effect. So, but if you look at the course and the calculation is done there, the only difference is that you won't have this factor of 4, because that factor of 4 came from from the fact that the temperature is spreading over the entire surface, but this one doesn't. And you can use that to calculate the temperature of the moon, and it matches like the maximum temperature of the moon that was measured. The last thing, this alpha, the way that you like, it's a parameter that you could kind of calculate. So you can maybe look at Venus and measure how much light is coming out. You can look at the moon or send like lunar missions that measure that, or you can send something out into space, measure how much light is coming into Earth and how much is leaving at the visible wavelength, and then gives you how much it gets reflected. All right, I hope this was useful, and I recommend you look at that course.